Hello. Today we're going to be talking about the chemical context of life. And I know you're thinking this is biology, so why do we care about chemistry? And well, that's because all matter in the universe is composed of elements, and that includes us. All plants, animals, all living organisms are just collections of atoms and molecules that are linked together through chemical bonds. And I'll be honest with you, when I was a student, I was like, okay, chemistry, I'm doing this chemistry, okay, whatever. But as I've grown and as I've continued my education, I really have come to see how important chemistry is in biology. If you really understand the basics about chemistry, you will understand so much better how biology works. So I'd encourage you to really embrace the chemistry, and it will actually help you become a better biologist. So this video is going to talk about basic chemistry, okay? And let me preface that it can get a lot more complicated. So the things you're talking about in chemistry class, I'm not going to go nearly in depth of that. This is essentially just the very basics of what you have to understand about chemistry in order to understand the parts of chemistry that are very important to biology, okay, to understanding biology. So it can get much more in depth. And yes, I'm absolutely going to simplify some things. I apologize for that ahead of time, but it's really just because we always know there's much more depth we could go into. So today we're just essentially skimming the surface and doing just the basics of chemistry. So living organisms are composed of matter, and matter is defined as anything that occupies space and has mass. So your pen has matter, your computer has matter, you have matter. In fact, you have mass, you have volume, you matter. Okay, so matter is anything that occupies space and has mass. So living organisms are composed of matter as well. Well, matter is made up of elements. And elements are defined as pure substances that cannot be broken down into simpler substances by ordinary means. Well, so elements are things like sodium and carbon and oxygen. Those are elements, right? There are these pure substances that can't be broken down under normal situations into simpler substances. And there are 90 naturally occurring elements and over 15 artificially synthesized elements, some of which have been made in a laboratory for only fractions of a second. So this, you probably are familiar with, this is called the periodic table of elements. And it is a way to organize all of the elements here on Earth from smallest to largest. So up in the upper left-hand corner, that's where we find hydrogen. Hydrogen is the smallest element. And then you go along in rows, or what we call periods, and that's why they call it the periodic table, because each row is called a period. So hydrogen is the smallest element, then helium, then we start with row or period 2, then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. We go to row 3 and we go on from there. So do you recognize any of the elements here, or maybe some of those that I've mentioned? Maybe you recognize helium, like we put in balloons to make them float. Perhaps you recognize carbon. That's a really important one. And oxygen. We need to inhale oxygen. We need that for life. Maybe you recognize sodium or calcium. There's copper. Maybe you recognize things like gold or silver or titanium, right? There's a lot of different elements. And these are substances, right? These are the substances you can't break down into simpler substances under normal means. So if you're not familiar, this is Chemistry Cat, and you'll see Chemistry Cat a couple times in this little video. How often do I like jokes about chemistry? Periodically. Ha ha ha, right? Periodic table, get it? They're as bad as dad jokes, aren't they? But they're fun. So living organisms, because again, we're pulling this chemistry back to life, to biology, living organisms are composed of about 25 key elements. And 4 elements make up 96% of the weight of living organisms. And those 4 elements are, drumroll, carbon, hydrogen, oxygen, and nitrogen. So these are the four elements that make up most of the weight of living organisms. I remember these four. It's a little silly. I remember these four because if you look at the abbreviations, carbon is a C, hydrogen's an H, oxygen's O, nitrogen's N, CHON, right? CHON. It's not actually a real word in English, but it sounds like it, CHON. Okay, so CHON, those are the four elements that make up most of the weight of living organisms. Now, there are 7 elements that make up most of the remaining 4%. And some of these are really important, and I'm sure you've heard of them, that they're important for you as growing individuals, right? Like calcium, you need calcium to maintain strong teeth and bones. Phosphorus, potassium, sulfur, sodium, right, which is found in salt, table salt. Chlorine, magnesium. These are the elements that make up the remaining 4% pretty much of the weight of living organisms. And then we have what are called trace elements. Now, trace elements are those things that compose less than 0.01% of living organisms. Now, these are things like chromium or iodine. So you don't need a lot of them, but you still do need a little bit of them. And how do we get these elements? Well, they're in the foods that we eat. Now, when we think about the elements like carbon, hydrogen, oxygen, and nitrogen, each element consists of one kind of atom. Now, an atom officially is the smallest unit that retains the chemical and physical properties of an element. But really, you know, what it is, an atom is sort of like the structure, the map, you know, and we can represent this with a diagram. Now, all atoms have the same basic structure, which has an atomic nucleus, which is surrounded by one or more electrons. Now, often we see an icon like this to represent an atom, where the atomic nucleus is in the center, and then we have these electrons that circulate around that atomic nucleus. And this is the general structure of an atom, although realistically, it's much more like this, right? Where we have that atomic nucleus, and then these electrons are circulating nearly at the speed of light around that atomic nucleus, sort of forming this, you know, cloud around them. The other thing is that the atomic nucleus takes up only a little bit, and then a little bit in the center of the atom, and then the electrons actually circulate really far around it. So if you were actually to try to make a better analogy than this, it would be like if you had a football field, and the ball in the center of the football field, or even the football stadium, the whole stadium, the ball in the center would be the atomic nucleus, and the electrons would be circulating throughout the entirety of the stadium. So when you look at it, electrons occupy almost all of the space of the atom, although the nucleus makes up more than 99.99% of the mass. Okay, so electrons are not very heavy. They don't have much mass, and they're nearly moving at the speed of light, really at a great distance from that atomic nucleus. So what is found inside of that atomic nucleus? Well, 2 particles known as protons and neutrons are found inside the atomic nucleus of an atom. Now, I want to take a second here because in biology, we hear the word nucleus a lot, right? Like, oh, the nucleus is that walled off portion of a cell where the DNA is found. And that is absolutely true, but that's the nucleus of a cell. We're talking about the atomic nucleus, right? The nucleus that's found in an atom. So within the atomic nucleus, we found protons and neutrons. Now, protons have a positive charge, okay? So they're positively charged. And the number of protons in the nucleus of an atom is known as the atomic number. The smallest atom is hydrogen, right? The smallest element is hydrogen, so hydrogen is going to have the smallest atom. It has an atomic number of 1. That means that hydrogen has 1 proton in its atomic nucleus. Now, of the 92 naturally occurring elements, uranium has the largest atomic number. It actually has 92 protons in its atomic nucleus. Now, also within the atomic nucleus, we find neutrons. Neutrons are called neutrons because they are neutral, right? So they do not have a charge. Whereas protons have a positive charge, neutrons are uncharged. Now, neutrons are usually found in the same number as the protons. And this is definitely the case with the smaller elements that we deal with in biology, like carbon, hydrogen, oxygen, and nitrogen, okay? So with smaller atoms, the neutron number is going to be equal to the proton number. Now, this does change as the atom gets bigger, okay? And in chemistry, if you take a chemistry class or watch a chemistry video, they'll explain why that is, but just generally, as there get to be more protons in that atomic nucleus, well, protons are positively charged. So, they start repelling each other because they all have the same charge. And so as there are more protons in the atomic nucleus, there end up being more neutrons than protons to sort of have a gravity, a mass to keep everything together in the atomic nucleus. Okay, that's just a summary of how that works. But with those smaller atoms, like the ones we find in biology, the number of protons is going to be the same as the number of neutrons. Now, an exception is hydrogen. Hydrogen is a special one because it has one proton, but it has no neutrons. So it's a very interesting atom. Protons and neutrons have about the same mass, okay, which we measure in something called Daltons. And so we can use something called the mass number, or the atomic mass, to represent the amount of protons and neutrons together. So the atomic number is the number of protons. The mass number, or atomic mass, is the number of protons and neutrons together. So if we look at the periodic table, here, this is just one element in the periodic table, oxygen. And so you can see there's a big O, that's the abbreviation for oxygen, and the name oxygen is under the big O in the periodic table. Above the O, at the top of the box, is a number, and that is the atomic number. So the atomic number for oxygen is 8. That means that oxygen has 8 protons. Now, here's the deal. Oxygen will always have 8 protons. Okay, it might have some extra electrons. It might end up with some extra neutrons in different situations, but it will always have 8 protons because that's what it is to be oxygen. Okay, so an atom of oxygen is always going to have 8 protons. If it has, 7 protons, well, now it's not oxygen anymore. It's a different element. The other number here you see is at the very bottom of the box of the periodic table, and it says 15.999. Well, that number down there is known as the atomic mass. Okay, so that's the atomic mass, or the mass number. That's the number of protons and neutrons together in an atom of oxygen. Now, I know you're thinking, well, hold on. If it has 8 protons, it should have 8 neutrons. So 8 plus 8 is 16. Why isn't the atomic mass 16.000? And the reason it's 15.999 is because there are elements out there known as isotopes. And isotopes are, this is an atom, okay? An isotope is an atom of an element, so like oxygen. And oxygen is going to have 8 protons, but these isotopes have a slightly different number of neutrons. Now, generally, isotopes are much more rare than the normal atom, okay? And you can see that, right? Because what they do is they're sort of averaging together all of the different normal and isotopes that are found out there at proportion. So you can see that there must be an isotope out there of oxygen at a very rare amount, where instead of having 8 protons, it has 7 protons, right? So when we occasionally average in a 7 there, well, 8 plus 7 is 15, so when we're doing the masses, this is the average of all of the different oxygens out there. So that's why it's not exactly 16, but for our purposes, we know that a typical non-isotope version of oxygen is going to have 8 protons, and it's going to have 8 neutrons, okay? Let's look at another one. Here's carbon, right? Carbon, the abbreviation is C. And carbon has an atomic number of 6. So it has 6 protons. 6 protons, thus it has 6 neutrons. So 6 plus 6 equals 12. 12 is the atomic mass. But again, you can see it's not exactly 12 because there are some isotopes of carbon that exist at a low frequency that also have 13 or 14 as its atomic mass because it has 7 or 8 neutrons in that atomic nucleus. So, it's always going to have 6 protons because that's what it is to be carbon. But sometimes in these isotopes, the neutron number is different. So maybe you've heard of carbon dating. Carbon dating is when we can look like 300 or 400 years, 200 years ago. We find something from that era and we can look to see how much of those isotopes of carbon still exist in that item. Because those carbon isotopes, they break down and they give off the neutrons, and we know the rate of that. So we know how long it's going to take for those to break down back to carbon with an atomic mass of 12. So we can use that rate to figure out how old things are based upon how much of those carbon isotopes are still found in that particular item. Now, isotopes can also lead to unstable atomic nuclei, right? And so they start breaking down and they give off energy when those isotopes break down. So we can have isotopes that are actually radioactive. They give off radiation when they break down. So things like uranium is, has radioactivity. And as it breaks down, it gives off this radiation, this energy. Okay, so in the atomic nucleus, we have protons that are positively charged, and we have neutrons, which are not charged. The number of protons is the atomic number, and the number of protons and neutrons together is the atomic mass, aka the mass number. Okay, so that's what's in the atomic nucleus. Next, I want to touch briefly on electrons. Now, electrons are those particles that are circulating at nearly the speed of light around that atomic nucleus. Now, electrons are negatively charged, and the number of electrons is going to also equal the number of protons in an uncharged atom. So for every positively charged proton, there's a negatively charged electron, right? So they balance each other out. They equal each other out. Now, electrons do not have much mass at all. Actually, they have a mass that's about an 1800th of the mass of a proton or a neutron. So they're very light, and they spend most of their time circulating in these areas around the nucleus. And these areas are called electron shells or energy levels. Now, we can sort of see that represented in our drawing here. Now, this is a very common way to represent the architecture or structure of an atom. It's called the Bohr model. And in this case, we see that in the center is where we find the protons and neutrons. And then here in this little circle, well, that's what represents that energy level or that electron shell where the electrons are going to circulate, which are found in gray here. Okay, so electrons are found in these electron shells that are found outside, circulating around a distance from the atomic nucleus where the protons and the neutrons are. Now, the electrons of an atom fill into these shells, and they fill into the shells in a defined way. For instance, in the first shell, you can have 2 electrons. That's the maximum, okay? So if we have something like carbon has 6 protons, so it has 6 neutrons and it has 6 electrons. That means the first 2 of those 6 electrons are going to go into the first shell. Now, the second shell, which is farther away from the atomic nucleus, can hold a maximum of 8 electrons. So any remaining electrons are going to be in that next shell. Now, if we're getting to bigger atoms, bigger elements, then there might be additional shells, okay? So the next shell after that can hold a maximum of 8 electrons until it is considered full as well. Okay, so the first shell has a maximum of 2, then it's full. The second is 8, the third is 8. And from that point on, it gets a little bit more complicated. And I will mention, if you've taken chemistry, then you'll have heard of these things called orbitals, because of course the electrons just don't go in a circle. You know, we like to think like this is the planetary system and it just goes in a circle all the time, but it's not only going in a circle. It goes in this entire shell, right, in certain shapes around the nucleus. And those are called orbitals. And you can check out different videos to learn more about these specific orbitals and how electrons circulate within them. For our purposes, we need to know that the first shell holds a maximum of 2, and from that point on that we're going to be talking about, the maximum will be 8. Remember that in biology, the elements that are found in living things tend to be the smaller elements on the periodic table, so we really just need to understand the basics to move forward with our discussion about how biological molecules come to be. So here's the top half of the periodic table of the elements. This is where most of the biological elements are found. So let's go ahead and practice how the electrons would occupy these shells around the atomic nucleus. Let's start with oxygen. Okay, so oxygen has an atomic number of 8. That means there's 8 protons, and that also tells us there are 8 electrons that are going to be found in those shells. Now the first shell can hold 2, right? That means that the second shell will hold 6 electrons. Because oxygen has 8 electrons, the first shell holds 2, and then there's 6 remaining. So 1, 2, 3, 4, 5, 6. The second shell then won't be full. 8 is full, 6 is what it has. And so what's going to happen is that these elements, these atoms, undergo interactions with other atoms, or maybe even the same atom, so that they can essentially, hopefully, get to a full number of electrons in the outer shell. Okay, because atoms are most stable when they have a full outer shell. So we'll talk about that in a different video if you want to learn more about how the bonds form between different or the same atoms. But oxygen will have 6 electrons in its outermost shell. And so the word we use to term that, it's called valence electrons. Okay, so the valence shell is the outermost shell that has electrons in it, and the valence electrons are the number of electrons in that outermost shell. So oxygen has 8 total electrons. It has 6 valence electrons because we have 6 electrons in the outer shell. Let's try another one. How about sodium, right? Sodium has an atomic number of 11, so it has 11 protons. It also, therefore, has 11 electrons. And those electrons fill those shells in the exact same fashion as we've described. So in that first shell is going to be 2, because there's only a maximum of 2 that fit in the first shell. In the second shell, we're going to keep going. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're up to a total of 10 electrons, 2 in the first, 8 in the second shell. Now, sodium has 11 electrons, so that means in that third shell, there's just going to be 1 electron. And when we start talking about the bonds that are important in biology, we're going to understand how that 1 electron often gets given away, donated, because that way sodium can have a full outer shell, and it's most stable at the full outer shell. We'll talk more about that in a different video. So the rules here, remember, are that the first shell holds a maximum of 2, and then the second and third hold a maximum of 8 electrons. Get it? What kind of fish is made out of 2 sodium atoms? Tuna fish? Chemistry cat is so cute. Look at that little bow tie. Okay, so the number of electrons in the outermost energy level of an atom, right, the outermost shell, determines how reactive it's going to be. So here on the left, we have argon. Argon has 18 electrons, which means 2, 8, and 8. Okay, so it has a full outer shell, full complement of 8 electrons. On the other hand, here's chlorine, which is abbreviated Cl. Chlorine has 17 electrons. And so it has 2 in the first shell, 8 in the second shell, and 7 in the third shell. And so argon is not going to be very reactive because it has a full outermost shell. right? So we call that inert. Argon is inert. It's not very reactive. On the other hand, fluorine doesn't have an outermost shell, so it is going to be able to create bonds to try to fill that outer shell with an electron to get to 8 electrons, and then essentially that will be the lowest energy state of chlorine. Okay, so these atoms are going to bond with each other in an effort to try to fill their outermost shell. And if it's the first shell, well, that's 2 max, but if it's one of these other shells, it's 8. 8 is going to be the magic number that they're trying to get to 8 full electrons in that shell. Now here is helium on the left, which is abbreviated He, and hydrogen on the right, which is abbreviated H. Helium has 2 electrons. So it has the first shell, 2 electrons in it, it is full. Okay, so helium is inert. It doesn't react very well because it has a full outer shell. Hydrogen, on the other hand, has a shell that's only half full. It only has 1 of the 2 maximum in this outermost shell. So hydrogen is very reactive. Hydrogen is going to participate in a lot of different bonds, and hydrogen is really important in living things, right? It's one of those top 4, carbon, hydrogen, oxygen, and nitrogen. And hydrogen will participate in a lot of different types of bonds because it's very reactive. It needs that 1 electron because it only has 1 out of 2 in that outermost shell. So here's a question for you, and pause the video to try to see if you can deduce and work through the answer to this. Here's the question. Assuming all of the following atoms are in a neutral state, that means they're not isotopes. They don't have an they're not charged with an extra electron or 1 missing electron. Okay, so they're in the normal state. Which of these 4 atoms will likely be chemically inert? Inert meaning not very reactive, right? It won't react. So pause the video, see if you can come to the answer, and then come on back. Okay, so we need to look at our 4 different options here. And we have to know, to be inert, that means that the atom probably has a full outer shell. So here in A is oxygen. So oxygen has atomic number of 8, has 8 protons, and here you can see it also has 8 electrons. So 2 in the first shell, and that leaves 6 in the second shell. So it's not going to be inert because it still has room for 2 electrons in that second shell. Here's argon in B, and argon has an atomic number of 18. So the electrons fill 2 in the first shell, 8 in the second shell, and a maximum of 8 in the third shell. So this atom here, argon, has a full outer shell of a maximum of 8. Okay, it has 8 valence electrons. So this is probably going to be the answer, which is chemically inert. But let's take a look at C and D just to make sure that the other answers don't make sense for being inert. In C, we have fluorine. Fluorine has 2 electrons in the first shell and then 7 electrons in the second shell for a total of 9 electrons. So because it has 7 electrons in its valence shell, it has room for 1 more electron, so it's not going to be inert. And in D, we have lithium. Lithium has 3 protons and thus 3 electrons when it's uncharged. So that means 2 in the first shell and 1 valence electron. So that's 1 out of 8. So certainly lithium will be very reactive, trying to fill that outer shell. Okay, so the answer here was B. Argon is likely to be chemically inert because it has a full complement in its outer shell, full complement of valence electrons. Remember, valence electrons refer specifically to the electrons in the outermost shell. So here's carbon, and I wanted to introduce carbon to you because carbon is one of the most important elements in living things. Carbon has an atomic number of 6, so it has 6 protons, and that means it has 6 neutrons and 6 electrons as well. So in the shells, there are going to be 2 electrons in the first shell, and that means 4 are left in the second shell. Now the maximum in that second shell is 8. So carbon is actually only half full. And that's why carbon participates in so many different interactions with oxygen, hydrogen, nitrogen, and other elements in living organisms, because it has 4 valence electrons and it essentially is looking to get to 8. So it's half full. It can have interactions with many other atoms. Okay, so carbon has 4 valence electrons. That means 4 in the outermost ring. I'd make another joke, but all the good ones are gone. Gotta love chemistry, Cap. So now that we understand the basics of what atoms are and how those valence electrons work, we'll next talk about the different types of bonds that can occur between atoms and various elements to try to fill that outer electron shell to a maximum for that particular atom. So we'll talk about things like covalent bonds, ionic bonds, hydrogen bonds, and other important interactions and molecular forces that essentially are found keeping the molecules together in living organisms. And yes, you absolutely can expect more chemistry, Kat, in our next discussion. Thanks for watching, and be sure to like and subscribe to my channel.